Hello, I'm Kunihiro Oshima from Kyoto University, and I'll start my talk about Flex-SNN, spiking neural network on flexible substrate. And firstly, I talk about the backgrounds of my research, and then I explain our proposed Flex-SNN model and strict implementation. And after that, I evaluate our Flex-SNN's inference accuracy and power consumptions. After that, I conclude my presentation. Okay, and our Flex-SNN is composed with organic thin film transistors. So firstly, I introduce organic thin film transistors. OTFTs are manufacturable on a flexible substrate at a low cost. So film or paper substrates are available into the low temperature and the low cost processes. So OTFTs are suitable and promising for flexible sensor systems. And such sensor systems will require an edge processor for real-time data processing or compressing communication costs. And edge processors will be needed, and edge processors should be low power, on-chip, flexible, and low fabrication cost. And so such backgrounds, we proposed Flex-SNN, that's OTFT-based spiking neural networks model and circuit. And the advantages of Flex-SNN are shown here. Our Flex-SNN can operate with low power consumptions due to event-driven spiking neural network. And Flex-SNN are manufacturable via an OTFT fabrication process because the Flex-SNN is composed with OTFTs and wire crossing, metal wires. So manufacturable via a simple OTFT fabrication process. And so on-chip and OTFT-based processors are achieved without an additional manufacturing cost. And also, Flex-SNN are scalable due to metrics like wire crossing synapses. Okay. Next, I show the Flex-SNN model structure. The left side figure show the Flex-SNN model, and the Flex-SNN model is composed with an input layer, metrics like synapses, and excitatory neurons. In data processing, the data images or the sensor outputs are converted to the input spikes in peripheral circuits, and then they are fed to the input layers. And the input spikes go through the synapse matrices and fires the excitatory neurons. And the firings of excitatory neurons are counted and aggregated to get an output input levels. And the weights of these synapse matrices are shown in the right side figures. These figures show the weight maps of for classifying the MNIST 0 and 1 data images, and each with 16 excitatory neurons, and each pictures for each different excitatory neurons connected to each different excitatory neurons. And these weight maps represents when the input, when the each excitatory neuron fires. In other words, when the input images similar to these weight maps shapes, then the inputs excitatory neuron fires. So firings of neurons change with input spikes. And synapse weights here are determined by offline training with a combination, using the combination of spike timing dependent plasticity rule and winner-take-all manner. And here I showed how to aggregate firings. As I mentioned here, the synapse matrix weights for each neuron are different each other, and these so the firing counts are also different, and these firing counts are used to obtain an average firing counts for each levels, and these average firing counts are used to obtain the compared and the largest aggregated firing count determines the infrared levels. And about the more number of excitatory neurons here, the excitatory neurons number is the 16, and the classification levels are only 2. This difference is for enhance the generalization performance. I mean that each, for example, these the leftmost and first from the left pictures are different but have same levels, and the these difference enhance the generalization performance because of the these slight chute differences. And here I show the devices used in the Flex-SNN circuit. The OTFTs and synapses are used in our Flex-SNN. The OTFTs are composed with AL gate, ALX plus self-assembly layer insulator, and Ornick semiconductor, and AU source and drain electrodes. And zero-wave synapses are composed with ALX plus self-assembly layer and AU stacks. And this structure is common to the OTFT's insulator. And one-wave synapses are composed with AL, CL, and AU. This structure is also common to the contact between the gate and top contact electrodes. So OTFTs and synapses share the same device structure, and so they share the common fabrication processes. And also these simple metal stacking synapses can be realized with metal wire crossings like this microphotograph. And in Flex-SNN circuit, the synapse weights are learned in the decimals or banalized using WTH. Specifically, in banalizing, if the decimal weight is smaller than the WTH, then the binary synapse weight becomes 0 and otherwise becomes 1. And here I show the neuron circuit structures. The left side figure shows the neuron circuit structures, schematics, and this neuron is composed with amplifier, level shifter, and ring oscillator. The synapse matrix output signals are fed to the VN, and these spikes are firstly amplified and down level shifted, and finally fed to the ring oscillator. And this ring oscillator's frequency is controlled by VN. And the right side of the figure shows the V-in and V-out signals. As shown in this figure, the V-out fires when the V-in is fallen, V-in level is fallen. Yes, so also these ring oscillators, in this ring oscillator, lower V-in, this is more frequent firings since the frequency is controlled by V-in. And then I show the evaluations. And here we evaluate the inference accuracy of Flex-SNN in circuit simulations. And the leftmost and the middle figures show the device characteristics used in the simulations. And all of the characteristics and zero-wave synapse characteristics can be successfully modeled as shown in these figures. And one-way synopsis characteristics and wire crossing resistances are calculated using the resistivity of AU and AL electrodes. And the inference accuracy versus WTH is shown in the rightmost figures, figure. And as shown in this figure, the accuracy increases with WTH, and 97% inference accuracy is obtained at WTH equals 0.99. And this results means the higher WTH improves the inference accuracy, and higher WTH makes the one-way synopsis more sparser, and sparse one-way synopsis reduces the snake passes in the Flex-SNN circuits. So the smaller number of snake passes is important in our Flex-SNN circuit for improving inference accuracy. And here I show the energy consumption in neurons. And this figure shows the energy consumption in neurons with processing 1 MST images. And we tested the 2,115 images. And all of these images can be processed with less than 2.1 millijoule energy consumptions. And this value is enough small to compete with other edge processors, we think. And finally, I conclude my talk. We propose the Flex-SNN model on circuits, and model on circuits. And Flex-SNN can be manufacturable on flexible substrate at a low cost. And Flex-SNN can operate with low power due to event-driven SNN and easy to scale due to simple metrics like synopsis. And we get the inference accuracy of 97%. And so we think Flex-SNN is applicable to ODFT-based sensor systems for processing signals. Okay, thank you.